Hello, everyone. So I'm Yoshitake. I'm from Japan. I'm a professor at Yamaguchi University. So today my goal is to introduce a new developed strengthening system. The keyword, the internal anchorage. And also we are focusing on the carbon fiber composite cable, CFCC tendons. The title of my presentation is Post-tensioning system for a carbon fiber composite cable tendon with an internal anchorage of concrete. Here is the content of my presentations. First of all, I'll explain the research background and objectives. And second, I'll show you our developed post-tension internal strengthening system. At the first stage, we used the steel rigid bar for press-releasing tendon, but now we are using the carbon fiber composite cable as a press-releasing tendons. And I'll show you the very fundamental test, that's a pull-out test, and we perform the FE simulations about the pull-out test. Research background and objectives. As well as US, so in Japan, there are so many deteriorated infrastructures. According to the Japanese government, so this graph shows the total number of the bridges 50 millimeter or 50 meter or longer. So most of bridges are constructed during the economic growth of Japan, such as the 60s to 70s, and now 140 bridges are more than 140,000 bridges. So Japanese civil engineers are tasked with maintaining and appropriately retrofitting these structures. But unfortunately, this is a typical accident of the old PC bridges in Japan. Unfortunately, this accident occurred in my hometown. So this bridge is, can see that this bridge supported the vertical PC bar and 18 vertical PC steel bars. These are anchored in the bridge abutment, and all PC bar corroded, and some bars suddenly ruptured. So the end of the bridge was uplifted suddenly. So unfortunately, a car crashed at the uplifted. So this PC bar supported in the straight hole grouted with grouted. I think the post-tensioning bar and anchor bolt generally fixed by grouting material, but mechanical anchorage is more reliable compared to the bond type anchor. So we need to develop a mechanical anchorage system. Next. So we developed a new mechanical anchor system, post-tensioning internal strengthening. The name is K-Plex method. As you know, compared to the conventional straight hole, so wedge-shaped anchor has a higher resistance to pull out. So I'll show you how to make the wedge-shaped anchors. First, so we made just straight hole, and the end of the hole, so we can make the here. Can see the we can make the wedge-shaped hole by using this special drilling device. Of course, and this drilling drilling device can be removed after the drilling. This is the detail of the drilling tool for enlarged hole tip. This drilling tool equipped with the tapered shaft and head is pushed into the drill, so segment for enlarge appeared here. I hope you can see the drilling tool for enlarged hole tip movie. Okay. So we can make the wedge-shaped hole by using this drilling tool. Very simple. And after the drilling, the enlarged segment can be set into the drilling tool. And of course, we can remove this drilling tool. Again, so I'll show you the internal strengthening system. As we make the straight hole and drilling the wedge-shaped hole, and grouted high-strength mortar as a filler, and insert the PC tendons. Here is internal anchorage system. After that tensioning, we can provide the pre-stress to the concrete member. This slide shows the high-strength mortar used in this system. This high-strength mortar has almost over 130 megapascal. It's very high-strength mortar. The unique of this system used just only very compact machinery, very compact, and this is a drilling device and compact machinery. Of course, this system can be used as a jointing the new and existing concrete members by using this system. This is a typical application for this system. For example, the footing of the bridge pier, strengthening here, or widening of the bridge pier, footing of the bridge pier. And now, so we are trying to use this system for the application for the bridge decks. For example, widening the slab wise by using this system, post-installed anchored and PC tendons. And concrete joint from this system may be much more durable compared to the conventional jointed RC structures. However, as you know, the bridge deck slabs are subjected to the colloid attack due to the de-icing material. So we need to reduce the risk of the corrosions. So we focus on the carbon fiber composite cable, CFCC, as a pre-stressing tendons. Perhaps the CFCC is a very famous in the country. I think so. But the CFCC is provided from the Tokyo Rope International. The mechanical property of CFCC is here. It has a very high strength, almost 200 kilonewtons, and it has a flexible, lightweight, and non-corrosive. But another concern appeared because conventional post-tensioning system, in case of the conventional post-tensioning system, we can grip the both sides of this PC tendon. But in case of the internal anchorage system, we cannot grip this side. So we need to find how to grip this PC tendons. So the problem is a proper fixing method for the CFCC end in the internal anchorage shaped. Of course, the CFCC cannot be applied the screw threading, and if we use the steel tube or terminal fixer provided from Tokyo Rope International, but these are steel materials, so it has a risk of corrosions. So finally, we found a very simplified method. Again, so the CFCC consists of the 7 wired. So to enlarge the diameter of CFCC end, the 7-strand cable is reversely twisted. Just reversely twisted, but increase the enlarge of diameter. So this is the concept of the CFCC in the wedge-shaped hole. This is reverse twisted chips and inserted the internal anchorage, wedge-shaped anchorage. So hereafter, so we conducted the very fundamental experiment to the pull-out test to determine the interval of the CFCC tendon or the minimum thickness of the RC slab. So we use the two kinds of the specimens, 200 millimeter or square and 150 millimeter square. This is a pull-out test used in my study. So three specimens for each side were tested. This is a pull-out test system. And here shows the pull-out test for CFCC tendons. So to provide the tensile force, we can grip by using the steel strip. This is not internal anchorage. Internal anchorage is here, and this is a sorry, no sound, but you can see that this is pull-out test. Okay, and we confirmed full grouted in the enlarged CFCC tip. This is a loading program and observe the Pmax maximum load. According to the manufacturer, Tokyo Law, the guaranteed load capacity is PU is here, 192.5 kilonewtons. But the Pmax is a test value. So in case of the 150 millimeter, the average value is lower than the 0.95 PU, but 200 millimeter square, it has a higher than the guaranteed load capacity. And this slide, this figure shows the end slip of CFCC tendon. As you can see, the observed end slip of the PC tendon is negligible, no slip. And this slide shows the elongation of CFCC tendons. The load capacity of CFCC tendons, it has a 20.5 millimeter diameter embedded in the internal anchorage, achieves a sufficient anchorage effect. And to confirm the stress distribution in the inside the reverse twisted chips. So we perform the FE simulations. Here is a reverse twisted chips, and here is a wedge-shaped hole. Here is a FE mesh and FE modeling for the CFCC pull-out test. These are the FE simulations here. Okay. So these are the CFC cross-sectional view of the CFCC tendons. These are the inside of the stress distribution. The maximum stress around the 8 megapascal. Again, so the compressive strength of the grouting material has over 100 megapascal. So the estimated stress was only 7% of its strength. So we confirmed this anchorage system can be used for the internal strengthening system. So I'd like to conclude my presentations. First, the load capacity of the CFCC tendon embedded in the RC block achieves a sufficient anchorage efficiency. And second, the minimum interval and applicable thickness of the RC member were designed to be the 200 millimeter. And the combination of the wedge-shaped hole and reverse twisted tip of the CFCC tendon is adequate for the anchoring. And last, the post-tensioning press-bracing system using the CFCC tendon can be applied for the strengthening RC members. Thank you for your kind attention. I think almost finished.
Yeah. half a minute to ask questions.
Very interesting concept. Simple.
Very simple. Yeah.
By two things. One is the length of the tendon, and the other one is when you reverse it, there's some randomness how the diameter is going to be. We have a process. You have to reverse it over this length and this diameter, so you get good response.
Sorry, so, thank you. Questions. The length is, sorry, I show you the where, yeah. Sorry, the length are almost 200 millimeters, and sorry, 20 centimeters, and the diameter is 3 times of the CFC, the wedge shape, sorry, reverse twisted chips.
20 centimeter?
Yes. Yeah. Depending on the CFCC run. So I show you the here. Sorry, I cannot use. So from here to almost 20 centimeters.
This can be used for in construction also, not just for
Yeah.
in construction.
Yes.
Some of my projects I have used Tokyo Road, business columns.
Yeah.
Both sides of this. So we have to use all the standard Tokyo Road.
Yeah.
And this one can be used for new construction.
Yes. But, of course, so it can be used for the new construction. So our goal is to strengthen the existing concrete. This is the first purpose. But second purpose, of course, we can use the new construction list. Sorry, finish. The chat is here. Sorry. No problem.